So today, Doug Hopkins is speaking. Doug is a professor of electrical and computer engineering and the director of the Laboratory for Packaging Research and Electronic Energy Systems, which is part of the Freedom Systems Center here at NC State, and is an affiliate faculty member of the Center for Additive Manufacturing and Logistics, also at NC State. Doug has over 20 years of academic and industrial experience in electronic energy systems. He received his PhD in electrical engineering from Virginia Tech and worked at the R&D centers of the General Electric and Carrier Air Conditioning Company in advanced power electronic systems for military and commercial applications. He was also the co-founder of Dense Power, LLC, a joint launch technology company. Dr. Hopkins has had numerous consulting projects with Emerson Electric, Grundfos, Lawrence Livermore Labs, Eaton, and Verizon, among others, and held summer appointments with the Army, NASA, and Ohio Space Institute. He's published over 100 journal and conference articles, a number recognized with awards. And with no further delay, Dr. Doug Hopkins.
Thank you very much, Rogelio, and thank you everyone for tuning in. As Rogelio mentioned, this is to update you on the project we have through PowerAmerica. I'd like to acknowledge the team members. Here at NC State, we have several very highly talented PhDs that are, and several of them are looking to graduate very shortly. Young Shu, he's the project director and is handling the fabrication of the module he'll talk about. Bo Guo, he focuses primarily on the power electrical systems and the full power test platform development. Xin Zhao has an interesting background, which includes material science as his master's and bachelor's degree. And he's very tied into not only the metallurgy problems we run into in our attachment materials, et cetera, but also gives us insight into other materials that we might want to consider. Now, this project is the TRL 4 and above, so we make notes on what we want to focus on through other research. Adam Morgan is also on our team. He's bringing with us more information about how to do wire bonding. And again, there's other ways of doing wire bonding. We call it flexible weld interconnects because we can only do round wire, flat wire, ribbon wire, but also we're looking at coil bonding. And of course, materials are looking. There's also materials in using copper, such as direct copper or copper clad with aluminum. But those are not part of this investigation, but we're moving along to develop those programs in parallel. The undergraduates we have working for us are Julian Comey and also Caitlin Golding. And Caitlin is also the supervisor for our packaging laboratory. The team members that from industry, especially USCi, that gave us the challenge is Anup Bala and Larry Lee, along with Shirley Zhang. And we talk with them, and they turn around and tell us, yeah, that's okay, but how are you going to manufacture it? So we're always keeping our feet on the ground. Also, CPS Technologies, we've been working with them closely because of their abilities to give us aluminum silicon carbide composites, but we also have parallel talks with them on using other materials such as pyrolytic graphite embedded within the systems, or even aluminum nitride captured or cast directly into AISIC, which is one of their technologies they offer. And then lastly is Hefty Mechatronics, and again, going back to a lot that Adam's been doing, is looking at alternative ways of being able to do bonding to our die. For this project, we're staying with conventional wire bonding, but we do control what the height is, and we'll get into discussing how we want to optimize the wire bonding. And then finally, a little bit, if you get online and look at what we do for PREs, we're trying to not only present it as just recently designated as a service center so we can provide services, but we also try to support an undergraduate student club. And we're also, this is a research test bed or a research resource so that we can do advanced packaging research within the lab. So the project, as posed by USCi, was to develop a 6.5 kV, 100 amp, and 200 amp SuperCascode module, but we wanted to constrain it to a 57 pack. So we're using a package that's basically built for silicon, but we wanted to cram in a lot of the SuperCascode devices to show the exceptional performance that we're seeing, and then also do a comparison of that to the traditional IGBT 250 amp module. So in support of the module, because one thing to electrically design and then physically build the module, but how do you do the test? And in that, we have half an effort going into developing a full power test platform, so it's going to be reusable. And when I say full power, this will be continuous full power testing for a 6.5 kV 250 amp module. And we'll talk more about that aspect of it. And by the way, we want to also note that we really do focus on how to support the DOE mission for workforce development and expansion of wide bandgap devices across the universe. So as an outline, we're going to talk about a physical module and how we designed it and the electrical aspects of it, the thermal aspects of it, and stayed with more mechanical, traditional mechanical approaches. And the SuperCascode module itself, because you're using several devices in series, as you'll see, requires a balancing circuit. And so the module essentially has the balancing circuit sitting in the center, and we can then have two parallel paths for power devices. And the devices we'll start out with, so this project actually has two phases to it. Phase one is to use these 1200 volt, 12 milliohm devices, JFETs. These are rated at 50 amps per die, and we have two rows of these. So we can do a 100 amp module single switch, or we can have a 50 amp, 250 rows that will give us a phase leg. And then we would drop in after that on a phase two. Phase two is all the same year. We're doing this all at the same time. Is a 1700 volt device that we would then be able to put in on, again, the same number, same both sides, but now we have a 100 amp per die, which will give us 200 amps per module, or be 100 amps to 100 amp paths for a phase leg. In the layout for the module is to accommodate the 1700 volt devices, the 1700 volt 100 amp devices. So that what happens then is with the 1200 volt devices, when we use those, we have a little bit more inductance in the module than usual, but you'll see later on that it's a perfect drop-in for the 1700 volt devices. And the design of the module is for 10 kV. So if we are able to even stretch these further, we can actually get to higher voltages. And I mentioned before, the second part is that we'll have a full power test platform, which is an independent test circuit, which we can do continuous full power testing. So I want to give you a little history of where this came from. The idea actually goes back to, I think, Infineon, started showing how to series up a bunch of, series up these JFETs, normally on JFETs, and then go ahead and use a silicon MOSFET to switch to JFETs. Now the cascode structure goes way back even to Jay Balaga had cited that earlier in some of his works, where he had a MOSFET, silicon MOSFET switching a JFET. But now we're taking advantage of a silicon MOSFET, very easy, very cheap, very fast, and we then switch the entire series of JFETs. And then JFETs, of course, are silicon carbide JFETs. The initial circuitry that you see here, the basic concept is that when you turn off the bottom MOSFET, then you basically, since the gate of the JFET above it, normally on device, have to have a negative threshold voltage. As you turn off the MOSFET, you then pick up you raise the source of the MOSFET, and as, of course, if the structure was already on, you start applying voltage across the drain to source of the MOSFET, therefore raising the source of the JFET in this case Q3, off of ground. And as you raise it up off of ground, its gate, though still tied to ground, presents a negative gate-to-source voltage, which is what you need for the normally on JFETs. And as you do that, that JFET turns off, which is Q3. You are then lifting up the source of Q2, and as you lift the source of Q2 up, you then, of course, you're going to tie this through a avalanche diode or a Zener diode effect, avalanche effect. You're going to tie that gate still tied relatively to ground, and you're going to then have the turn-off of Q2 because the source is rising higher than the gate. And then when Q2 starts turning off, you then are doing the same thing for Q1. You're raising the source up, and then the gate is clamped through D1 and D2 to a certain voltage distribution, and therefore Q1 turns off. But in that, you have the fact that the distributions of the devices in somewhat of a static form are determined by the avalanche ratings of the Zeners, D1 and D2. Now, you go into more detail in the fact that, well, this is okay, but what about dynamics? Because when you start going to very high-speed switching, you have to wait for charging currents through the junctions of the devices to be able to start turning the devices off, and some devices will rise too quickly. And so in a dynamic sense, what Cwr's team did, is they added an RC, which then slows and makes sure you equalize the turn-off of all the devices. And then during turn-on, you have a charge source to be able to get the devices to turn on relatively quickly. The assessment of this early was that the layout is relatively difficult, especially from a packaging point of view, and the bias voltage is leakage current dependent. So you need to look at this as though you're leaking through your junction. So when you look at all these, if you're going to do this kind of analysis, you want to look at these devices not as being perfect on-off switches, but they have a finite resistance and they will have a finite leakage current, and you need that to be able to operate these circuits. Last year, 2016 at APEC, USCi presented their variation of this circuit, and they had a little bit different approach to how they do the dynamics within the system. But in this case, you're required to use relatively high voltage capacitors. As you can see, R4C1 is a relatively high voltage capacitor. And if you really kind of get into laying this out, it does not lend itself to an easy layout. So not to diminish the effectiveness, because this is a very, very effective circuit, we took a little bit of a different approach and analyzed what we really needed to have. And notice on this one, for instance, on Cwr's, we do go gate to gate with the Zener. For ours, we made a modification and looked at how to be able to combine the devices, and also how we would do that within the module as far as module design goes. What we'd like to do is to have primarily all of the circuitry. The circuitry is broken up into basically three parts. You have your power stage with your power device in series. You do have resistors, auxiliary resistors, that are going to be a little bit warmer than normal. So we take those and put those onto the DDC, and then we have the rest of the balancing circuit, other than the power device, the balancing circuit, and then we go on to something inexpensive like an FR4 that we're using, or we can even go into Flex. So in this case, you see one of the two iterations we use, and this would give us very easy mounting of the balancing circuit and interfacing it to the power stage. And the diodes D1, D2 could either be hooked gate to gate, or it can be hooked, as we see here, center tapped on the balancing circuit on the RC. So if we look at this, we have the fact that it gave us much easier thermal solution that we needed to have, because we can actually balance the devices. In the typical structure, the lower Q3, the lower JFET, can take up to almost twice the amount of power loss as other devices, so we can balance that a little bit easier. We also have a more simplified PCB board layout. In fact, we are able to combine the board layout to have two separate functions with the same layout. And we don't use high voltage capacitors. And that latter part is rather important because we want to keep the cost down, and we want to be able to make sure we can use the FR4 approach or flex approach. So that gave us, so from the NCSU topology, which is a combination of the two previous ones, we then use this then to start looking at, well, what is the electrical performance, what is the thermal performance? And then again, as I mentioned, we didn't do anything special, this TRL4 didn't do anything special as far as the mechanical side goes. We're trying to stay with relatively straightforward routine processing approaches. So these are, when you get the because this will be made, this talk will be made available to you, and so you'll be able to see the three in comparison. And there's a lot of, and obviously there's going to be a lot of similarities because we put them together. So this is kind of the general layout of where we're going as far as the packaging side goes. What we have is, again, in the upper left corner is the 57 pack. That's the footprint. We got to fit within that. That means you're going to have a base plate you can bolt down, room for the bolts. You have to have enough creepage and clearance. This is a 10 kV design that we're going for, even though we're only operating at 6.5 kV. And then also, if you look at how we lay things out on the inside the module, the upper right corner, the upper right picture is essentially what we've been sending out and having fabricated as far as the different pieces go. If you notice, we're going to go with an AISIC base plate, and in fact, the AISIC base plate is actually going to be both a flat plate, so you can mount it to a chill plate, or we'll have direct, and we'll have samples that will have correct pin-fin cooling, and that would be for fluid cooling. So we're actually going to drop this into a cooling chamber. Or, I'm sorry, we're going to drop this onto a fluid cooling system and directly cool the base plate. And what that allows us to do is actually run this at even much higher power levels than what you normally would, and therefore we can test this. We can really extend the testing of the power devices. Remember, we have a full power test platform. We can run the devices at much higher power levels because we'll be able to drop the cold plate temperature to extract more heat. Okay, so the upper right side, the other part of this to note is going to be how we have to terminate. You want to terminate in such a way to minimize inductance. Again, it's a silicon package, and so the height is something we're stuck with. The terminal placements we're stuck with, etc. So here we have the layout and bringing the, as you'll see later, bringing the terminals back over the current flow path to be able to have some cancellation of the electromagnetic fields, which gives us obviously a lower inductance because we have lower leakage inductance, lower stray inductance. In the bottom right is a very close-up, and now I'd like to point out that if you see the light gray, obviously we're looking at, in the bottom right corner, you have a base plate, you're putting DVC in the base plate. On the top side, brown shows your DVC pattern layout. And in the pattern layout, you also see these lighter gray chips. Those lighter gray chips are the 1200 volt devices. When we go to the 1700 volt devices, the 1200 volt devices are 5.5 by 3.5. Or 5.3 by 5.5. So they're smaller, but the 1700 volt devices are 8 by 8, 8 millimeters by 8 millimeters. And they'll fill up pretty much the entire width of the pad. And of course, you have to leave some room on the pad because you have to make you have to use bonding to get, you have to use an interconnect to go from the pad to the next chip because these are all in series. And so if you look at how it's interconnected at the top, and I was trying to pull the curve, here it is. So you look at the top, you'll see that you have to bond from a pad onto a device. So in your pad, you'll need a little bit of space to be able to fix your interconnect, and the rest of it then would fill up the 8 millimeter by 8 millimeter. And that's a big move because we're going from a 50 amp device to a 100 amp device on this design. If we look at, I asked USCi to give us some cost estimates because everybody asks what's the cost, where's it fit? and what's the performance like. So we're essentially using, on ours, we're essentially using the 8x8 chips, the 1700 volt chips. These might be a second generation, so they're a bit even better. But essentially, this is the data that we use. But they're going to be using a half-bridge module, and they're comparing that to a half-bridge MOSFET module. And if we look at this, at the amount of die that are being used and how you're going to be able to finish all this, for them, again, we're using the same die, they'll be using, in their case, because they're using a phase-leg module, half-bridge module, then what they'll do is they'll have 2 sets. We use 10 die. We use 10 JFETs. In our module, you can see on the right-hand side, you can count them up. We have actually 2, 4, 6. We actually have 6 shown here. And here we're going to have, for our module, we'll have a 50 amp on each path. And if we parallel those, which is one of our layouts for our DBC or for our balancing circuit, then that would be a 100 amp module. Or we could run 50 amps, because we print our own housings, and so we could redo our terminations. And so we have the ability to terminate and actually do a phase leg at 50 amps. We drop in the 800 amp or the 100 amp die, and then that gives us a 200 amp single switch module, or we'd have 100 amps on each side for a phase leg. They're going directly to the 200 amp phase leg module. And the cost, which is what the initial question was about, was basically they're projecting for their module $11 an amp versus $20 an amp for a 6.5 kV MOSFET chip. And if we look at the switching speeds and switching times, and particularly the capacitances, device capacitances that you relatively see, we see that we actually have and can switch much faster. And so it gives us a tremendous leg up. And we're really excited about taking our module and running it to the extremes in switching and in power limits. And the upper right corner is their picture that they're using for their half-bridge module. And it's the LIN pack. So, balancing networks. This is the simulations we've been doing. I'm showing only for the 1200 volt devices. We also have those for the which is 50 volt devices. We also have for the 100 amp devices. We do the testing at 5 kV, 50 amps. We run this right out up to 100 kilohertz, a 50% duty cycle. And the inductance that we need to add in is being added in as a lumped inductance, but we've done modeling, multi-physics modeling, to be able to get an estimate of what the inductance is going to be throughout that. We'll show you some resistance and inductance calculations, simulations and calculations later. But under this test approach, the simulation approach, using the models given to us by USCi for their devices, we come up with a power distribution of the devices as shown here. Now again, notice that on the 86 watts is that lower JFET. And so you try to use the balancing circuit to somewhat mitigate that and spread those power levels out a little bit more. And the 7.2 is the power loss within the silicon MOSFET. So here we have an estimated 442 watts total loss within our module for a single side, and that's about 0.8%. In fact, actually, I should double this, 0.36, because it's a single side. About 0.4% of the loss of the modules of the total power process would be lost in the devices. And we're looking at switching times with all of our inductances, capacitance, et cetera, of around 40 to 50 nanoseconds on and off. Mentioned that and mentioned what the power is. Now, what's very interesting, and we don't show it because of time, is that this is due to the 1200 volt device. Again, it's a 0.53 by 0.35 millimeter device. If we pop in the bigger device, 8 millimeters by 8 millimeters, then this changes substantially because the larger area. We have a nice graph that shows how much better we're going to have going to the 8 millimeter by 8 millimeter. we're quite excited about being able to get the higher power levels. So I said that. So here's the layout for the printed circuit board, and it uses we actually balance along the center. We balance both outside, so you're actually having cross balancing. You know, the devices are in parallel, and you have cross balancing with the center balance board, the balancing circuit. And so the balancing network design is for up to 2 parallel strings, which we have. We can run them independently or run them together. High power dissipation resistors are placed on DDC, as I mentioned before. I've shown you where those went. And the printed circuit board can actually accommodate 2 different balancing circuit designs. And one is with the diodes gate-to-gate, one is with the diodes center tapping the dynamic balancing RC networks. The backside is shown here because this sits in the bottom of the module and is actually sitting on the DDC. So it's sitting on the AISIC. So if it sits on the AISIC, then of course if you have any coupling coming in, you have high voltages on your printed circuit board, you have to be careful that the printed circuit board can take the high voltages at the high voltage end of the stack. And so we really will end up doubling the size of this board and specifying high voltage laminate to be able to allow the printed circuit board to sit in the center, sitting directly on the base plate. And then eventually for mass production, you just do a 4-layer board. For us, you do a 2-layer and just add in an extra spacer board, which is just another laminate board. And so that's what this is about. Okay. So now we get to the interconnect resistance I mentioned before, and this is very important. I mean, when you're designing your modules, designing your circuits, we do not have perfect conductors, you know. And so when we draw our circuit and schematics, you know, oh yeah, we got a line goes from this component to this component, and we never think about what the resistance is of that wire, but it's finite. And so when you're laying out your module and looking at what you have to be able to get the resistance down, you have to start right off the bat, even when you do a full circuit. You have to say, what is going to be my loss budget? I don't have, you know, zero resistance wires and zero inductance interconnects. So in this case, we said we want to have the total module resistance to be no more than 10% of the total on-state resistance for all the devices. Now this is 10%, this is substantial, but we can knock that down further if we go into a little bit more aggressive packaging. Remember, we're stuck with a silicon package to start with. And also this drops substantially when we go to the 8mm chips because we have extra, this is for the 1200 volt devices that are small, we have a lot of extra copper sitting in series and we can't get away from that. So if we were to drop in the 8x8mm chips, then this resistance drops substantially. And I don't remember what the number is. Yeah, I don't remember the number. We don't remember what the number is. One of the questions then is, well, how thick should the DDC be? Remember, you're designing it for scratch. How many wires do you want? How big are the wires, et cetera? And in this case, we're looking at, we did the analysis. And we really like to have as many wires as possible. That's typically what you like to do. It helps to keep the current down per wire, so therefore you have more reliability in the interconnect. You also have redundancy in the interconnect. It has all kinds of good things, and also spreads the current better within the devices in the pathways. So we said, okay, under 10% and maximum number of wires for the criteria is 4 12mm wires bonding onto a 12mm copper. And that's what we're going to go with. We could get it lower, but again, TRL4 and above, we are keeping in mind what would be a good standard practice, best practice in industry. We did electrical potential distribution, so we're seeing how the actual fields distribute within the module. We have to make sure that they're keeping our voltages within certain limits. And this is what these are about, and of course we're staying well within the limits that we need. We do have here at PRES, we've developed, because one of the things that PRES does is device testing for high voltage devices. We support Dr. Balagan and Dr. Misra and Dr. Huang we support them by, they develop a high voltage device, how you're going to actually do, it's one thing to probe it, but how do you actually get in and do some actual power measurements? And so we have packages that we drop those devices into, and they can go ahead, and the package is well qualified, well understood, well characterized, and they can do their testing. What we do here is we have an encapsulate material that we work with Walker with, and that encapsulate allows us to go to 10 kV, do 10 kV plus type of modules, but more importantly, it also goes to 225 degrees C, which is something we're looking at, not part of this program, but we could actually push this to higher temperatures, depending if we finally use silver mount down rather than solder mount down for our devices. Now, along that same line, one of the areas that I've been, this is not just this project, this has been something I've been doing for quite a few years, is trying to find from the manufacturers who actually do DDC, what volts per mil or millimeter will their DDC substrates take. Because we only use, for instance, 25 mil ceramic because from manufacturing, it's robust. We could go down to 10 millimeter or 10 mil ceramics, but you need to be very careful how you process it, and you have to be careful how thick the copper is on top. And it all lies in the fact is that in the copper on the DDC process, copper on ceramic, in this case, ALN needs it Al2O3 in order to be able to bond. You can see that it's not a smooth surface, it's ragged. Well, for electric fields, you now have field intensity, these spires, you have these field intensity points, and those field intensity points are what actually can break down the ceramics for our DDC. So I still have not been able to get a specific data sheet, and I'd love to have somebody send one to me, a data sheet that actually traces back to standards that can say, yes, this is how many kV per millimeter we have in our material for breakdown, and then be able to use that to be able to scale the different thicknesses of ceramic, because ceramic is one of the biggest thermal drop points within our structures. So all that said, I am posting here from Cwrsion, Rogers Corporation. The fact is that they actually did PD testing, partial discharge testing, and established that they can go at 14 kV per millimeter at less than 5 picocoulombs in 5 picocoulombs, you're actually counting the number of electrons flowing through, which is then you can use this then to say, okay, this is the kind of voltage withstand I can have for my module. So under this, the 25 mil or 635 micron thick ceramic we're using, ALN, should be able to withstand our 10 kV design. Okay, AISIC, the base plate, it's being fabricated, and what they do is they have AISIC, which then gets sprayed with copper, and then we'll see, that's why you'll see a large copper plate or copper metallization on this. And then we'll have it, we'll pattern it, and then we'll drop in and solder on our DDCs, and then we'll epoxy in our printed circuit board, and then do wire bonding. And then also we have, this has been specified to them for pin fins, so that we can then go ahead and do pin fin cooling, direct water cooling, which gets us to what kind of resistance do we have within the structure. If we look at just junction-to-case, we're taking a module, building a module, you go to clamp to a cooling plate, and you have to use some kind of tin material, some kind of thermal interface material. When we do it, we're going to use the indium heat spring technology, which is actually it's an indium-based fine wire mesh that you drop in, and when it compresses, it fills in all the voids and gives you high thermal conductance compared to any of the metal-loaded epoxies or thin thermal greases. And if we look at this and do the analysis, we can see plugging in all of our different losses within our devices. This is the high end, and this is the low. And JFET1 is the low voltage, is the lower end of the voltage string next to the MOSFET, but has the highest power loss in it. We can see that The worst case is we're looking at about 0.43 degrees C per watt from the top of the die to the back side of the AISIC. And then for the low voltage MOSFET, it actually is, because the FET's smaller, you actually have a higher resistance. However, you only got 7 watts, so that's a non-starter. So that's if you're looking at junction-to-case. If we decide to go to water cooling, then it becomes a lot different. Now, our simulations show going from the hottest chip into the water. We used water for the cooling. We actually have 0.52. So the previous slide, remember, has to be sitting on some kind of tin material, and then you're going to have some other kind of heat extraction. Here, you're going directly to your cooling fluid, and it's at 0.52. Mentioning before about the 2 different types of devices, here's a wonderful example of going from small area die to large area die. And you can go ahead and take a look at this. This is about where we put our distances between our die to make sure that we don't have thermal interface or thermal interference between the die. But as you can see, we have a whole different set of numbers, a much better performance for the larger size die, 8 millimeter by 8 millimeter die, and therefore we can push these to much higher power levels. So I'm going to be doubling the current, going from a 50 amp device to a 100 amp device, but if you notice, I'm going from a 0.45 down to a 0.2 in thermal resistance. And so now I'm going to be able to actually go push this module to even a little higher power levels than before. And also because of large die, the thickness of the ceramic isn't as critical because you've already spread out as much as you can with the top side copper. Okay, that takes care of the module itself. Then we get in the full test platform. And what we have here is, it goes back, research I did earlier, and I developed a whole set of cascaded topologies for pulse power. And the concept is that, well, if you take a buck and a boost, we know that if you take a buck, use duality, you get a boost. You can take a buck and you can then cascade it with a boost, you get a buck boost. You can also do a boost and a buck. And if you, at that point, you can then start saying, well, I have rules, and there was a thesis done on this, where I can hook the output back to the input. Okay, well, why do you want to hook the output back to the input? Well, what it does is it recirculates energy, and you start pumping energy within the structure. And you can reduce this to some of these you can reduce down to these cascaded structures down to a single device. But you pump energy, and so, well, when you pump energy, what are you going to use it for? Well, one of the things is flash lamps and your cameras, et cetera. You're going to use it for pulse power applications where you're going to do a railgun or other things. So what we found is, what we were able to show is there's a whole set of pulse power topologies that now can be linked back to a direct approach on how to derive topologies. So we may have even derived a couple extra pulse power topologies at the time. But that being said, the work was originally stimulated from work I did with the Army on wanting to test these big GTOs, and they had this couple megawatt cooler sitting outside with resistor banks, and they said, what can we do better than that? And I said, well, let's start looking at some of these, came up with these topologies. So that's where this is. It works fairly simply. You can close one switch. You can start pumping the current up. As you open the switch, you'll then go ahead and charge this capacitor. As the capacitor charges, you can then close this switch, which allows you to charge that inductor, and that inductor starts to circulate current. When you open that switch, that inductor at the top, L2, will then go ahead and, if Q1's open, it'll start feeding the capacitor C1. And as you open Q1, you also are feeding capacitor C1 from the left inductor, L1. So both L1 and L2 are able to feed energy into this capacitor, but more importantly, the L2 keeps getting pumped up and higher currents in it. And so therefore, you can have very, very high currents flowing into this in the circuit, and even through Q1, if you'd like, with only having to have a very, very small source at the very beginning. This source, V1, only needs to be, all it's going to do is supply losses in all the components all the active components and all the passive components. That's the purpose of V1. Now, Bo got a hold of this and started looking at how he might want to do it, and he redrew it. The bottom one is exactly the same topology. But he said, well, let's start talking about a little bit different. If I can use a fixed voltage, because we're only 10 kV and we have 10 kV power supplies in our lab, then I only need to have one that's high enough voltage, high enough power to be able to supply the system. And so we're using this as the topology where we're able to now pump energy into this topology, and we have very, very, very high current gain. I think it's in the it's double digits and maybe 30, 40 times current gain. Isn't it in that range? I think it is. But the voltage is going to be fixed at whatever we put in for the power supply. So this is the topology that we're building. It will allow us to be able to pump tremendous amount of current, high currents into our modules. It also is stable, which is really critical. We can get into a continuous mode, so we're just continuously feeding power into our devices. Q1 is going to be the device under test. In fact, I should go to the next one, simulation. So here we have the device under test. And that device then would be our module, and then of course over to the one in the upper right-hand corner does not have to be as high performance, but it will be the one that circulates the energy and builds up a tremendous amount of currents for us to be able to supply into the DUT. And on this topology, we also have a boost circuit, so we can go to higher voltage from a low voltage source, and so we don't use a 10 kV source or 10 kV with sufficient amount of power. Then we'd have to use a boost stage, and that's all we have to the left. So the way this works is the low voltage on the left feeds V1, gives you a boost for a high voltage. So we could go to 10 kV, go to 50 kV, 100 kV, et cetera, just rearranging our devices and make sure you have high enough voltage devices in the circuit. For the boost stage, DC bus voltage controlled by the input sensed at VS2, and the input current are sensed to provide protection. However, Q2 is the device under test, and it has an arbitrary gate signal that you want to run because you're testing it from 10 to 90% duty cycle, and then you take the other device, Q3, and you let its duty cycle to be defined by the kind of amount of current you want in the device under test. So when you go back to these slides, read through it, and see how it works, that's basically what you're doing is Q3 maintains the current at high levels, and the DUT switches as if it's in test mode. What's interesting about this module, or about this test platform, is it can actually you can actually separate out the losses you're going to have under continuous flow, because it's continuous current, and you also can look at just switching losses, because you can just run this at very, very fast duty cycles and back out switching loss and conduction loss separately. I put in here how this is almost finished. This runs through how the topology works. I don't need to go through this. This is something you'll have afterwards, but it basically says if you want to build your own, it shows you how to be able to not only how it operates, but also how to build it. And this is, again, more of the same situation. Advantages, the DUT runs continuously, unlike the pulse tester. It can characterize thermal and reliability performance because it's full power continuous, and it can simulate actual world use cases. So we can go ahead and run it and give it different load profiles. It also runs at arbitrary frequency and duty cycle, so that's pretty much open to whatever you want your DUT to do. The circulation part of the circuit it's built to respond to very, very high frequency. I think our design is shooting for a 1 megahertz design. We're using Litz wires, a lot of very close, tight interactions. It's going to be sitting in a tank of oil, so we can go to very high frequencies. We also can emulate zero voltage switching half-bridge topologies. This is the simulation of it, how it works, and this is holding it across, better part of a millisecond, having continuous current flow, etc. The last part of these last few slides are talking about the power test platforms controllers, and we also list here the kinds of features we have with the controller, with the control board. Again, if something you're interested in, we share this. You can see how we're building our boards. These are all been built and tested, and this will give us control for our boards. And this is on the MCU. Bo had said it was built in fabric that can be used to implement real-time overcurrent-based desaturation protection. And I know that there's a lot more of the terminology of how we're designing circuits, a certain fabric of the circuits, and I think that's a wonderful concept for people to be grabbing. Safety is a very, very big problem for us. Let me say it differently. Safety is a really big challenge for us, so it's not a problem. And so we're going to, if you look here, we have triple redundancy because we're going to be we have to come out to the outside one way or another, so we're using a lot of isolators, both wireless and photonic isolators, so that we can do our measurements and control and make sure people stay around a while. But for the graduate students, not that long. And the last slide, very last slide, is this is our overall process flow and how we're putting it together. It's important for us to have this because as you go along, we have to choose the right solder hierarchies. We've got to be able to make sure terminations are there. We need to do some pre-testing and post-testing. And so we have this all put together to figure out how to be able to put the whole thing together. And that is the end of the talk.
Thanks very much, Doug. Thank you. That was very good. We have time for a few questions, and because there's so many people logged on, please use the chat function you'll see in the dialog box at the top of your screen, and I'll be happy to answer any questions that you have. Well, I'll repeat the questions, and then Doug will answer them. What I meant to say. Are there any questions? If there are no questions, then we'll adjourn the meeting. Let me just wait another minute, though, to make sure that no one is trying to get through. Okay, I have the wrong screen open. Getting echoing period. Okay, that was a question about a noise problem. Never mind. Okay, if there are no more questions, then thank you very much for joining us today. As I said, the next webinar, someone asked, is it encapsulated? I don't know what they're referring to specifically.
Yeah, the module will use the encapsulate we use. It's a Walker material. It's good for, we've had it up to 12 kV and 225 degrees C. That's for the module. For the full power test platform, that'll be sitting in a tank of silicone oil.
Second question is it a spray copper?
Yes, yeah, it's a what is the high velocity HVFOC, whatever those words are. Yes, it is.
Okay.
Sprayed copper. Routine process. And the mask it, use a metal mask over it, and then you can spray. You notice there was a square and two circles. You basically have a metal mask. You stick it on top of the AISIC. They use the high velocity metal spray, and because of the high temperature and the way it's done, it makes a very strong bond of copper to the AISIC.
Thanks. Okay, if there are no more questions, we'll adjourn. Thank you all for joining us.
I had a question. There was a slide where you showed 457 watts per centimeter square, and I was wondering with the cooling that you're capable of doing, how many watts per centimeter square can you dissipate? And I'm looking for a rough answer.
So from our computational dynamic simulation, we get a junction to liquid thermal resistance for about 0.5. That's based on the die size of 5.5 by 3.5. So that's about 1/4 of a square centimeter size. So if convert it to 1 square centimeter, that's roughly about 4 or 5 times better, which corresponding to 0.1 something degree C per watt for liquid.
Okay. So the question was, on a slide I showed, because I just did a straight calculation of the watts on the device divided by the area of the device, came up with about 445 watts per centimeter squared.
Yes.
Right, because people are talking about kilowatts per centimeter squared now. And the calculation, if you were to do the calculation of thermal resistance and break it down, because we're doing the liquid, we're going to break the liquid, you get someplace, if you scale to a centimeter, which is the key, then you get someplace around a 0.1 degree C per watt as you scale your thermal resistance to larger areas. If you're a little careful, because the way you know, I'm looking at the die and what it's doing, but if you scale it on a per centimeter squared basis, it's scaled to about 0.1 watts per centimeter, or 0.1 degrees C per watt per centimeter. And so therefore you'd be able to get 445 watts, then you'd be increase about 40 degrees C, about 40 degrees C drop.
Okay. So in principle, you can do 450 watts or 447 watts per centimeter square, but you're going to experience a 40 degree C increase in the junction temperature. Is that what you're saying?
Yeah, into liquid, temperature difference.
Yep. Yeah. So the comment was then you'd be having about for 445 watts, you'd add a 0.1 degree C per watt. You'd have 44.5 degrees C between junction and liquid. So we're not going to air, we're going right to liquid.
Right, with liquid cooling. So
liquid
cooling you can do for, and the reason I'm asking is, you know, false chips, right? And if I can get 1,000 watts per centimeter square, then my chip is a 100 amp chip. 250 watts per centimeter square, then that same chip is only a 30 amp chip. And if I can get 500 watts per centimeter square, then I can rate that chip to 50. So the more you can dissipate, because silicon carbide, you know, the bottleneck is the heating, the more you can dissipate, the higher the rating of the chip you're making. And as far as commercial packaging is concerned, the rule of thumb that I've been given is that you can dissipate about 250 watts per centimeter square. So that's why the 447 kind of struck me as a higher.
That's water cooling.
On the higher side.
The water cooling.
Right. Okay.
And also when we package devices, we don't necessarily, you know, the manufacturer puts it in and has to put into a standard package, do a standard rating on the data sheet. But we're more concerned of what the pulse current rating of the device is. Because then it kicks in all the reasons why you don't want to burn up the traces on the chip, you know, that's all that stuff. Because we control, if I go to flip chip, if I go to wire, if I go to foil bonding, or I start going two-sided bonding, you know, I'm pulling so much heat out from both sides, I can afford to be able to run that chip to you know, fairly high current densities. And then it's up to the chip people, to then say, okay, well, the degradation over time running it at close to our pulse current rating is going to be this.
And there's actually,
yeah, that's
how high you want to run the chip.
You're right. Right.
Okay.
For current density. Yep.
Okay, thank you all for joining us today. As I said, the next webinar will be on Wednesday, April 5th with Virginia Tech presenting. So have a wonderful day. Thanks for joining us.
So